That's on. So that's on.
Okay.
Let me just test. Test.
Which one?
Yeah, it works.
Okay, let's put it off because off.
Good morning, ladies and gentlemen. Good morning. Welcome to those of you who aren't on the permanent programs at the Institute. My name is John Fulton. I'm the director, and it's my happy job to welcome you all today. I want to ask you for your forbearance during this week because we have two big programs, both of which are of interest to you all, I think. One on the mathematics of liquid crystals and the other on the mathematical sciences of complex fluids. So the program is, there are two workshops, one in the Institute main building, and this, which is one of the main lecture theatres in the Centre for Mathematical Sciences, where the undergraduates of Cambridge University are taught in mathematics. It's especially important for the smooth running, for your convenience, that the program should be more or less in parallel, and I would urge all chairs to stick to the timetable, because some of you may want to bolt to the other room, and people may want to come over here. So it's not rudeness to tell people to finish, it's simply practical. So I ask you to bear with that when and if it happens. Very briefly, the Institute is the National Centre for Mathematical Sciences Research in the United Kingdom. It's in this, what could be regarded as a mathematics campus of the University of Cambridge, all the buildings. This is the main building, which has the restaurant above. On either side, there are 6 or 7 pagodas and different subjects, geometry, analysis, cosmology, and so on, to do with mathematical sciences. In the corner of the campus, there's the Institute Research, where I work. There's a very large round building next to that, which is the Mathematics Library of the University of Cambridge. You're all welcome to visit there to take advantage of the periodic excursions. It's a very comfortable place. It's a very quiet place in which to read. I'm not going to delay you now because I've already emphasized the importance to stick to timetables. I would remind you that I believe that all of the information that you need, the practical information about your week here, about the dinners, about lunches and all of that, have been sent to you already by email. So I would urge you, please, if you're in doubt, to ask your colleagues what they read when they read the email, or what curriculum email you got back. Circumstances, I don't suppose you do either, but I understand that everything is there. So welcome. The role of the Institute is to facilitate research. Our only thoughts this week is to make your lives as comfortable as possible.
Okay, I have been asked to provide a background and historical review of liquid crystals. This is a pleasant task. I thank the organizer for asking me, but maybe for many of you it will be something which is very well known. I hope I shall interest the other people. Where is
No, I think that's on. That's fine.
That's this thing?
That's
Oh, yes.
the
Okay.
point.
Okay. We start with these two people who are the pioneers in the field, Georges Friedel and Charles Frank, which after a gap of 50 years take the work again. Georges Friedel was mostly a crystallographer, but he is the inventor of the notion of defect, but this was in liquid crystals. He made a large number of light optical observations, and we are continuing today to do optical observations, more refined. And thanks to these observations, he was able to make a classification of the structures of liquid crystal. This was after Otto Lehmann's work, 20 or 30 years after him, but he was able to do this classification. Lehmann did not C. Charles Frank had a paper, a unique paper, which boosted again the subject of liquid crystals and liquid crystal defects. In the meantime, the question of defects was the domain of dislocations in solids, and this was much developed, and Frank was one of the leading pioneers in this field also, and this is probably why he was able to discuss liquid crystal defects. Well, there is the influence of his work on dislocations, which is visible. So let me show you 3 slides of what those people in Friedel's times were able to see and from which they deduce the classification. These are smectic, in a smectic liquid in which the molecules are perpendicular to the layers, fluid layers, and you see there are defects which are very regular. This one here, these are perfect ellipses with focus, one of the foci, and perpendicular to the plane of the ellipses, one observes hyperbolae, which can exist over hundreds of microns, very much perfect. Another type of defect which have been observed are in nematics, which are fluid system without any repeat distance. And you see here defects which are flexible, thick defects, and thin defect, thin here, defect. So 2 types of defects, and on one of these thicks, you see a constriction, to which we shall come back. We can also see what they call nuclei, and they are also of 2 sorts. I'm not according to the way the black brushes rotate under the optical microscope when the cross nickels are rotated. And this is another type of structure, cholesterics, in which you have the molecules are chiral, and there is chirality at a macroscopic scale. So this is the axis of helicity, and there is a pitch, which generally is in the visible, so you can see it under the microscope. You see half a pitch here, also here, and you see in these pictures 2 types of defects. These are dislocations of the set of layers due to the pitch, and this is a disclination, which is another type of defects, which I'll discuss very much. But cholesterics there is a large zoology of defects in cholesterics, mostly discussed by Bouligan, but I am not showing here other pictures of cholesterics. So, okay, so we see, we conclude that we have in fact 2 types of defects of what we have seen. We have defects which are flexible, like in nematics and also in cholesterics, but to some lesser way, as we shall discuss later. And what I call isometric textures, which are these focal conic domains we observe in smectics, and also developable domains we observe in liquid crystal when there are 2 repeat distances, 2 discrete repeat distances. I call them isometric textures because we can explain all these very regular objects, like ellipses and hyperbolae, by assuming that the layers in the focal conic domains keep parallel, and that here the two-dimensional crystalline repeat distances keep constant in the deformation. We shall see that next. So let us first comment the isometric texture. This is you see the essential is here. You have parallel layers. The normals are straight lines. They envelop two focal surfaces. There is here one. And these two focal surfaces at their positions where the radius of curvature of the layers is infinite. So this region should be as small as possible because there is too much energy concentrated here. And the best would be, of course, that the two focal surfaces be degenerate to two lines. And when you impose this restriction, you find that there is a very simple family of surfaces which obey this condition, which are called Dupin cyclides, 1810 approximately, Dupin theorem. These are simple realizations, a cylinder with nested layers, tori with nested layers, and in the general case, you can demonstrate that the two focal lines are an ellipse and an hyperbola, which are conjugated, which means that the focus of one is the apex of the other. So this is a general picture. Physically, when observe layers with either negative Gaussian curvature or positive Gaussian curvature. This is due to some inequality on the elastic moduli, which I do not discuss. An object like this one, which would show two types of curvature, is never observed. But Randy will tell us much more about liquid focal conic domains. He has done recently a lot of work on them with his collaborators, very elegant, and I am not going more. I'm not saying more. So this is about the second type of isometric texture. We have generally hexagonal liquid crystals with a plane perpendicular to the columns, which are liquid. In this observation, which is due to Oswald, you can show through the theory that the columns are evolutes of cross sections of the cylinder, which is seen here end on, and the layers and the planes perpendicular to the columns are along the tangent planes to the cylinder. So in this geometry, the distance between the columns in these planes is conserved. This is an isometric deformation. In the general case, you have a cuspidal, you have some line, you consider the osculating planes to this line, and this will be the planes perpendicular to the columns. They envelop a developable surface, and you see something, the columns are like that, perpendicular to these planes. And in the previous picture, the developable surface was a cylinder. In the next picture, the developable surface is a cone. We have made the complete calculation of the distribution of the columns where the developable surface is a cone. And according to Nastishin, this is such a situation which is pictured here. Now, let us discuss flexible defect lines. And I mentioned the existence of point defects. And also defects of other dimensionality. And I go to sensible. Okay. So this is a crash, this is a very quick reminder of topological theory of defects. There are the following ingredients. First, there is an order parameter space. This is the space of all the possible different orientations and positions of the order substance in its ground state, obtained by rotating and displacing this ordered substance in Euclidean space, for example. So there is the appearance of the group of Euclidean space E3G. H being the symmetry group of the substance, which is called also the little group. This order parameter space is a quotient space, V equal G over H. It is the set of the left cosets of H in G. And each left coset being represented by a point in V. Now suppose you have a defect, L. This defect can have a dimensionality equal to 0 if it is a point, 1 if it is a line, 2 if it is a wall, even 3, but I shall discuss 3 a little bit later. And what you do is you made a circuit around the defect. In the case of a line, you make a circuit like that one, and you consider the variation of an image of this circuit in the order parameter space. So you have an image of this circuit in the order parameter space, since each point of this circuit is a different position and orientation of the substance. So this circuit will be a line if it is a line defect. It will be a sphere if it is a point defect. It will be a set of 2 points, one on each side, if it is a wall. And, and then you consider the homotopy classes of V of the images of those circuits. And they belong to the homotopy classes, pi 2 if it is a point, pi 1 or pi 0 if it is a wall. These are groups, and all these groups are abelian except the first one, called the fundamental group of the order parameter space, which can be possibly non-commutative. With interesting. Okay, so let me develop a little bit these ideas for the case of a nematic. Okay, if you consider the free energy of a nematic, assuming all the elastic constants equal, you find that there is a solution which is of that kind, where phi is the angle of the director with some fixed direction, and theta is the angle in the plane of definition. So, and you get, with different value of n integer, picture of that kind with a singularity along a line which here is perpendicular to the figure. So this is clearly the possibility you can get in 2 dimensions for a nematic. Here you see you restrict the director to 2 dimensions, 2-dimension deformations, and easy to see that the order parameter space must be a circle to which point any possible direction of the director, and the pi 1 of a circle is equal to the first homotopy group is equal to z, so which corresponds to all the possible value of n. Now, if you go to 3 dimensions, if you allow the director to escape in the 3rd dimension, as Meyer has coined it, you see that the director, for the case of integer lines, and only for integer lines, for -1, +1, -2, +2, can escape in the 3rd dimension and the singularity disappear. These lines are corresponding to the thick lines which were observed in the picture I showed you, and the thin lines are corresponding to declinations which are -1/2, +1/2, and which are where n is odd. So this was known. This was a remark which was done first probably by De Gennes and then Meyer-Cladis. Oui?
If you started with, say, a +3/2 declination,
Yeah.
would there be a sort of escape into the 3rd dimension by which it could go down to a +1/2?
Yes, I think so. Well, probably what will happen, you will have a separation in 1/2 and +1.
And then the 1.
Yeah. I think so. Well, it might depend also on the elasticity of the system.
Right.
For example, in this system, if you have rigid polymers, and thank you for your questions, this process might be not existent, because with a rigid polymer, you create a bend energy here, which is very considerable, and which in fact can be much larger than the core energy. And this has been observed by Masley in, I don't remember which polymer, Vectra, I think. I don't remember which one. Okay, but you can escape either upwards or downwards, so you can have singular points, and these are the kind of singular points which are along the thick line, and they can be, and this is what we observed in one of the first picture, and the constriction along the thick line is most probably an object of this type. So what is the topology of this object in 3 dimensions? Now the other parameter space is something like a sphere for all the directions of the nematics, of the nematic director, but 2 antipodal points will correspond to the same director. So in fact, it's half the sphere with antipodal point on the boundary identified. This is called the projective plane, and this is the ratio of the SO3, the rotational part of the Euclidean group, divided by d infinite, the rotational part of the group of the nematic. And you have only 2 types of defects. I'm sorry, the 2 should not be there. It should be, well, just the same. So you have one trivial element and one element which corresponds to the 1/2 lines. And in fact, all the 1/2 lines are equivalent. This was first shown by Bouligan in this very nice set of drawings. He assumed that you start from a... I'm sorry, I don't see my light.
Do you want to use a stick? There's a stick over there.
Yes.
Would that be easier?
Yes,
then you
probably.
may have to clip your microphone into your belt so you have one hand free.
You are right.
So, can you clip that in? Is it going to work? Or into your pocket, perhaps? Clip it onto the side of your pocket. There it is. There we go.
Thank you very much.
Now the microphone has come off. If you put that back, we had it. Other speakers note you might want to just.
Okay, the picture has disappeared.
Sorry?
It's also handy for crowd control.
We were sitting right.
So the picture, okay, this is the picture. Okay, here you have a 1/2, and here a -1/2, and you can show that you can pass smoothly from one to the other by using some escape in the third dimension by a smooth rotation, which is not the same for all the director around the line. So this is a direct proof that, in fact, you have only one kind of defect in a three-dimensional nematic, and this is nicely proved by the topological theory. Okay, so I want now to comment some properties coming, resulting from this topological theory of defect, and then I shall discuss other points. So first, about the non-commutativity, the typical liquid crystals whose fundamental group pi1 is non-commutative are biaxial nematics, first shown by Toulouse, cholesterics. Helium-3 was at the time also discussed, and the fundamental group is a group of quaternions with 8 elements and 5 classes of conjugacy. How do you classify the defects? In fact, each type of defect is represented by a full class of conjugacy. So in fact, you have only 5 types of defects in all these systems. One of these class of conjugacy being the 0 element. For example, what does it mean is that consider two lines, L1 and L2, with elements E1, with classes of homotopy E1 and E2, and rotate L1 about L2 by a complete turn. L1 will come back to its former position, but homotopically it will have changed its class of homotopy to an element which is in the same conjugacy class and which is of this shape. Another element coming from another property coming from a new non-commutativity is what happens when two defects are crossing. If L1 and L2 are two defects which do not belong to the same conjugacy class, when there is some obstruction to crossing, and the appearance of a line in between, which is represented by a commutator in the fundamental group. Okay, all these properties were discovered very soon after the appearance of a topological theory, but to the best of my knowledge, you might tell me if I am wrong, there are no experiments showing how it works. And I think that these experiments are all wanting. Now I come to configurations. Configurations are corresponding in a three-dimensional space to the third homotopy group. In a configuration, what you do, you take the space of dimensionality D and you compactify to a sphere by assuming that at infinity all the points are the element, the orientations and position orientation are the same. So homogeneous at infinity. If you can do that, it's very interesting to consider pi d, if you are in d-dimensional space, of V of such a system. The first time this object appeared in the literature is probably in a Finkelstein and Missner paper on the Sine-Gordon equation, assuming that in this one-dimensional case, the 2 points are infinity are the same. and they got a topological classification of solitones. In 2 dimensions, and assuming a three-dimensional nematic, S2 and P2 are the same when you consider this group. They just give the same homotopy classes. Belavin and Polyakov gave a classification with analytical description of the configurations in 2 dimensions for a 3-dimensional nematic. And this corresponds exactly to what we can see in the nematic capillary, where the one thick were observed in details by Cladis and Williams. Okay, this case is much important. So again, pi3 and S2 and pi3 or P2 are the same. So this might correspond to the third homotopy. So this corresponds to the third homotopy class for a nematic. And this is something that you can observe, in fact, in a cholesteric. In a cholesteric, there is a direction which is more important than the other, which is more physical, which is the direction of the director. In fact, locally, the order parameter is a trihedron, but you have special observational effect with the molecule, the direction of the molecules. And if the molecules is perpendicular to the sample in the direction of light in the optical microscope, you can see objects of that type which are corresponding to 3-dimensional defects, but you see here only the part of the defect which is corresponding to the local nematic director. And what is important is that this these homotopy classes correspond to Hopf mappings. They, I think, will be discussed in this workshop, so I'm not going in the details, but what you can see, the Hopf mappings are points on a sphere, S2, which project on S3, along which project on S3, and they have, in fact, pre-images in S3. And this is exactly these pre-images that you can see here. So you have here different Hopf mappings, which have been analyzed. I should have put the references, I am sorry, by Bouligan, Derrida, and Toulouse, and Pomo, maybe, in 1778. I think it's a very important paper which started the study of maps in liquid crystals. Now, I would like to go a little bit beyond. There are 3 topics here which, just for sake of completeness, I have here indicated, but which will not be in my discussion. Also because there has been, at least for these 2 first topics, a very vigorous development of experiment and theory recently. I am sure this will be discussed by other people here. And about integrability conditions, it is something which appeared in the literature 30 years ago, which has not been developed, which correspond to the fact that when you are in a system with discrete repeat distances, like a smectic, an hexagonal liquid crystal, or a 3-dimensional solid, any deformation which is supposed to be smooth must respect some conditions. For example, in the case of a smectic, it's n dot curl n equals 0. And when you do some, let us say, deformation, and these integrability conditions are not compatible with all the configurations that you can obtain through the homotopy classification. In fact, I don't consider myself that this is a very serious impossibility, because after all, even if these integrability conditions are not satisfied, they correspond to the presence of densities of defects, dislocations mostly, and they can be added to the picture we can have of configurations. I discussed in more detail frustration and interplay. Frustration. The term was introduced by Anderson and Toulouse for spin glasses, and there are at least two situations in which the notion of geometrical frustration, which is a bit maybe more precise than that one of Anderson and Toulouse, are interesting. This happens when locally the interactions between the molecules of the atoms are so strong that they are not, that they lead to the formation of local domains, which in this case cannot extend through state, which are not compatible, let us say, for example, with Euclidean symmetry. For example, if you have a situation locally in 2 dimensions which tell you that you like to have pentagons, which are with atoms here at the vertices, these pentagons, of course, do not cover space, 2-dimensional space, in a regular manner, and you need to have locally a defect where these 2 edges are glued together, and this is typically a disclination which happens here. In 3 dimensions, it's the same. If you have this would of course be correct, will be perfectly this perfectly tie a 2-dimensional sphere. A 3-dimensional sphere can be perfectly tied with regular icosahedra. You often have locally in, let's say, in amorphous system, symmetries which are locally icosahedral, and so they cannot extend through 3-dimensional space. And if you want to flatten, you can ask you a question, how to describe an amorphous system with local icosahedral character. You need to introduce disclinations in a somewhat disordered manner. In fact, there are situations in which these disclinations, if they are introduced in a regular manner, yield to ordered phase, Frank and Casper phases 58, are tied with disclinations which are regularly disposed. And this was recognized that there are disclinations in these Frank and Casper phases much later by Nelson and by Sadok separately. For the case of the blue phases, the interesting point, the interesting phase is the blue phase. Locally, they like to have double twist the geometries. The directors are along cylinders of that kind. Here the director is vertical along the central line and rotate along any radius to get something which has this geometry. But this cannot extend through space. It will destroy this nice local geometry. And in fact, the system is made of these double twisted tubes which arrange along generally a trihedron, a rectangular trihedron. And here you can see that you have a defect of a type minus 1/2 of a nematic type. So here too in blue phases, which can be regularly assembled. So you have three-dimensional crystals. You have a regular distribution of declinations. If it is not regular, you have what is called the blue fog. Okay, this can be represented also in a curved space, as here we had a curved space. And there is a nice representation in S3, which was proposed by Setna, in which the molecules align along Clifford parallels. And this is also an image of a hop vibration, in which if you introduce defects, you are supposed to go back to a blue phase or a blue fog. Okay, now I would like to discuss, this is my last topic, the interplay between dislocation and declination. And this is an important case because this cannot be easily discussed with a topological theory, although it is very important. In fact, we have to go back to a classification, a mode of production of defects, which is much older, which is called the Volterra process, and in which the elements of symmetry of the specimen are directly used, not the fundamental group. We are speaking of defect lines, of course. So assume that you have here a disclination corresponding to some rotation omega present in the system, and here the opposite disclination. You see that the product of two rotations at a distance AB is a translation. It's geometrically easy. And you get something of that kind, a displacement B, which I have written assuming that omega is small, but it does not matter. And this is corresponding to a dislocation because it breaks the symmetry of translation. And so this set of two defects is equivalent to a dislocation. The same picture can be slightly transformed in this one, in which this disclination is brought here. Omega has changed its sign because the direction of the defect itself has changed its sign. And you have here a dislocation, the same as here. So these two cases exist. Of course, they can be described in topological terms with a topological theory of defects, but it's much more difficult and much less interesting. So this is the first case where you see you have two disclinations of opposite signs which group to form a dislocation of Burger's vector L1, L2. And you can, according to the distance at which they pair. And the other case, this one, has been observed by Oswald in a columnar phase. You have here the two disclinations and a set of dislocations which attach to this part and which we have analyzed this way. In this former picture, in these previous pictures, omega and B were quantized. Assume that B is not quantized. For example, in a nematic, B can take any infinitesimal value. But you can have exactly the same analysis if you consider 2 points M and M plus dm on a curved line of disclination with the same omega at the origin of this disclination, then in between you have attached a density of dislocations. The point which is important here is that dB, this analysis to be valid, must be an element of symmetry of a system. In a nematic, any dB, any translation is a translation of symmetry. The nematic is amorphous from that point of view. So this is a way of explaining the flexibility of the lines in a nematic. In a cholesteric, not all the dB are possible because there is a direction where you have a quantized repeat distance. And it happens, in fact, that you cannot deform a line in a cholesteric at will, just because of this, the fact that you cannot add any kind of dislocation along a line in a cholesteric. So this will be mostly what I have to say. I would like now to conclude by a few points. Of course, there is important success in mathematics, algebraic topology, differential geometry, and 2 days we observed that geometry is revisited at a very fast rate. And this proves, of course, the vitality of this concept, and I'm sure it's not finished. Most of the experimental methods are still methods of observation, which, of course, are supplemented by a lot of progresses. What I will regret is that there are a few topics which have not been discussed in the last years, which would be interesting, or not enough discussed, which would be interesting for the future of liquid crystal defects. First, there is the question of the cause of defects. As I mentioned on a question of John, the core of defects, for example, of polymers is a very subtle problem, but it's also true in any liquid crystals. This kind of study has been much developed in solid crystals. There are, of course, a few theoretical work. I think the work of Slukin, for example, but there are others. Another point which, from my point of view, is not enough developed is the experimental rheological properties of defects. There is a paper by Christophe Blanc, he was one of my students, on the crystal plasticity of smectics, but it's practically all. And in this discussion, the Volterra point of view must be, the Volterra process point of view must be critical. And just to indicate it, dispiration have been observed mostly in Japan, I think, but they have not been really studied in detail. Dispirations are objects which have at the same time, in the Volterra point of view, a translation Burgers vector and a rotation vector. So it's a mixture of dislocation and disclinations. And I am pretty sure that the rheological properties of these objects should bring us very astonishing results. I think